Thank you, Sumitra. We continue our chapter on interpolation on Rkhs. We studied one result, but in that result, we assumed that there is a solution. I mean, just to fresh our memory, let me recall that result. So recall. As usual, H is an Rkhs, and on a set X, we consider a set of finite points, x1 up to xn in X. And the crucial point here is that we assume, so this is assumption, there is a G, well, there is a G in H such that G at point XE is equal to something given. I mean, it's called lambda. I should add here lambda 1 up to lambda n, arbitrary in C. I mean, no restriction on that. So existence is a part of as important hypothesis here. Then when we consider the projection of G onto the subspace created by kernel function at point x1 up to xn, and we called it PF of G, then PF of G is the, we have two things here. The first one is uniqueness function of, and the other thing, minimum norm. In H, which does the same job. Such that this function PFG at point xi interpolates the same points. I mean, I equal to 1 up to n. So if a solution is given, we know how to find the best one. We just make the projection. But now the question remains when the solution exists. And for that, we have a new set of results. For a matrix A, say an n by n matrix, the set of point X such that AX is equal to 0 is usually denoted by, I mean, said to be the kernel of A, but here we have kernel for another purpose. So the authors have used the notion null space. So N of A, null space of A is equal to this. But if at some other text you see the kernel, do not mix the two concepts. And here is our first proposition. The proposition is easy to prove, but inside the proof, there is an identity which by itself is very important, and it will be needed several times today and in some other demonstration later on. So here is the proposition. So the same assumption, X a set, H is an Rkhs on X. x1 up to xn in x distinct point. And here is the result. Then, if omega, and in the book it's written omega, I prefer to call it vector alpha, but anyhow, I mean, the book it's written omega. The vector alpha, alpha 1, alpha 2, up to alpha n is a vector in the null space of, or in the null space of the Gramian of k, xi, xj, I and j, both of them from 1 up to n. Then, so you see, up to here is just linear algebra. You have a matrix n by n, and alpha is in the null space. It means that if you can call this g, g times alpha bar is equal to 0. I mean, very, very simple thing to verify. But look at the result. Then the function f equal to sum alpha j k at point xj is identically 0. It means as an element of a space H. So so there is a simple consequence of that. So consequently, if we have 2 points, I mean, call them omega 1, or as I prefer, well, let's stick to the notion of the book. Omega 1 equal to alpha 1 up to alpha n, and omega 2 beta 1 up to bn, such that this matrix, the Gramian matrix, kxi xj times omega 1 is equal to kxi xj times omega 2. Then, look, omega 1 is not necessarily equal to omega 2. They can be two different vectors in Cn. But when they applied, I mean, when G acts on them, they create the same vector. G times W1 equals to G times W2. Then these two vectors create the same function, the sum alpha j kxj is equal to the sum beta j kxj. So the important thing here is to note that, as I said, these two vectors are not the same. The coefficients could be different, but at the end, when you do the summation, they create the same thing. You have seen this before. I mean, an example which I have mentioned repeatedly. Let me in the chat. I think that the null space is better than merge and kernel because null and 0 is. Yes, I mean, Sheldon says that the null space is a better terminology because null means 0. I agree with that, but for operator theory people, I mean, they use kernel for the, for the null space of an operator. I don't know what is more common, Sheldon, in linear algebra. Could you clarify, please? In linear algebra, do they say null or do they say kernel?
I think we see both, probably about equal. Maybe even kernel is a little more common. But as you said, it's ambiguous. Kernel has a totally different meaning when we're talking about an integral operator. So that's very confusing. Really? And it doesn't convey any sense of what it means. Whereas null, everybody knows null means 0. So it really fits much better. So I'm trying to get people to use null space all the time.
Sure, that's very good comment. Thank you. But maybe, as you said, equal, that's the influence of operator theory people that repeatedly they use kernel. And as far as I know, kernel means at least 3 different things. 2 of them we have seen here. There is one more, which is related to the kernel function, the kernel that they use in integral formulas. But still, it's not 100% the same thing. Well, yeah, I agree. Null space is bad. So about this proposition, it's kind of a long proposition, but the second part, if this equality holds, then we have this identity is immediate from the previous one because you simply see that K acting on W1 minus W2 is equal to 0. Therefore, here, if instead of alpha j, you write alpha j minus beta j, then the function is identically 0, which gives us this one. So we can have, for one function, we can have different coefficients. And we have seen this before, for example, in Sobolev space 4 or 3, one of them, when f of 0 was f of equal to f of 1. So for example, for the 0 function, we can say that 0 times k at point 0 plus 0k at point 1. And we also saw that k0 is equal to k to 1. So here is another representation. The coefficients are 1 and minus 1. And for the other one, 0, 0. So here, alpha 1 and alpha 2 make a vector, call it W1 and 1 minus 1. Another vector, W2, 1 minus 1. These are not the same. But if you make the 2 by 2 matrix with x1 equal to 0, x2 equal to 1, it's very immediate to see that this identity holds. So in other words, that 2 by 2 matrix acting on W1 gives the same acting on W2, and the result will be 0, 0. It's very easy to verify. So even though we already know based on other things that this identity holds, the proposition also tells us that, this holds. So this is not something new for us. We can have different representation. But why is this true? Why, if there is something in the null space, the function that it creates is identically 0? And this is based on an identity, as I said, which is somehow very important. And I believe the identity by itself should be mentioned as a lemma because we use it many, many times. So proof. Let alpha 1 up to alpha n be in C, arbitrary. Not the one which is in the statement of the theorem, and consider and let f to be the function j from 1 up to n, alpha j kxj. And now compute the normal f in h squared. This is not something difficult. Normal f is F inner product with F in H, and we can use the formula J from 1 up to n alpha J kxj. We have seen this formula before, but I want to write it differently the way it will be beneficial for my application. Kxi in H. Make the expansion I from 1 up to n, J from 1 up to n, alpha I bar, alpha J, kxj and kxi in H. And the last one, we have seen up to here before. Alpha I, alpha J, and this is K at point Xi, Xj. We have seen up to here before, but now I want to write this differently. I want to write this as the inner product. Inner product usually is the curly one. The inner product in Cn of what? Of the matrix K Xi Xj Ij from up to n, acting on the vector alpha 1 up to alpha n, again scalar product with alpha 1 up to n, alpha n in Cn. In simple words, if I mean, using G could be misleading because G is for any combination of Xi and Xj and with any n, but still, please allow me to write G. This is G alpha bar and alpha bar in Cn when G is in this matrix. So I write this again. This is the important formula that I will need. If F is equal to the sum J from 1 up to n alpha J K Xj, and I call alpha to be the vector alpha 1 up to alpha n, and G be the n by n matrix K Xi Xj 1 to n, then the normal F in H squared is the inner product of G alpha and alpha in Cn. That's the formula I need. And the proposition comes immediately from this formula, because in the proposition, we assume that omega, which is in alpha bar, is in the null space of G. This is our assumption. And therefore, G times L acting on alpha bar is equal to 0. So it gives normal F in H is equal to 0. So F is identically 0 in H. End of story. Immediately comes from this yellow formula if we pay attention to the form. And you will see that I will use a couple of more times in what follows. So knowing this, now we go for our theorem, which is the main theorem of this section. It's called Interpolation theorem. Interpolation in Rkhs. And the difference between this and the one we started at the very beginning, indeed it was a recall from last week, we want to remove this assumption. We want to know when there is an AG such that it holds. And for that, here is the result. The same setting as before. X is a set. H and Rkhs on X. And the finite set x1, xn in X distinct. And omega, yeah, well, doesn't give a name. Lambda 1 and lambda n, some points in C. Doesn't give a name for the time being to this. And then the result, then there exists. So see, it's an existence theorem. Then there exists a G in H that interpolates this point such that G at point xi is equal to lambda I from 1 up to n. You see, up to here, it's a question about Rkhs. You are looking for a function in that space. But now look at the characterization, if and only if. Now we move to linear algebra. The solution exists if and only if the vector lambda 1 up to lambda n, now we call it v, if and only if the vector v lambda 1 to lambda n is in the range of the matrix G. Belongs, I write it, is in the range of kxi xj so the existence is equivalent to being in the range of a matrix. The question which was in Rkhs is moved to another question in linear algebra, which is, I mean, usually easy to verify. An n by n matrix is given. We can calculate it easily, and then verify if this vector is in the range or not. Moreover, I mean, based on our previous result, when we know the solution exists, moreover, in this case, if we choose omega equal to alpha 1, alpha n, such that this G, well, no need to mention from 1 to n. This G times omega gives V. In other words, omega is a solution of that question in linear algebra. If omega is any solution, up to here, look, the omega, we know omega exists, but it's not necessarily unique. We saw in the previous proposition. Yet, if we choose omega such that then H equal to the sum j from 1 up to n alpha j k x j is the unique. Omega is not unique, but H is unique. Unique solution function of minimal norm which interpolates. Well, let me add in H. It's clear, but it's still to emphasize in H such that H at point xj is equal to lambda j, the one we were looking for. Satisfies the same thing that we wanted, but with two more properties. It's unique, minimal norm, and even we can calculate the norm. And the norm in H, again, this is something which happens in the in our RKHS. We have seen several examples before. It can be an integral formula, it can be a series, but whatever it is, the theorem says that it's equal to the inner product of V and W in Cn. Again, another connection to linear algebra. So in other words, it's a precious theorem, this one. It connects an interpolation theorem to a question in linear algebra. And moreover, when we know the answer is positive, it gives us a function h, which is unique. It has minimal norm. And also, without going into detail of calculation in h, we are able to calculate its norm just as an inner product in Cn. Well, wonderful result. So let me highlight what we have here. We have uniqueness, we have minimal norm. Oh, that's not good, it's too much color. Maybe yellow is better. We have uniqueness, we have minimal norm, and also we have a formula for the norm. So now, why? Let's see why we have this praise. We have, I mean, everything, all the tools needed to prove our result. First, I mean, it's an if and only if. For one part, assume that G in H such that G of xj equal to lambda j exists. Then we saw before, it was last week, that if we have a solution, when we project, then H defined to be the projection of G into the finite space F. F, recall that F is a span of kxi, x1 up to kxn. It's a finite dimensional space. We saw last week that if we have a solution and we project, the projection is still a solution. So P of F, which is the H, which is the projection, still is the solution. We have then G is also an interpolating function. What does this mean? It means two things. First, because of the projection, there are constant. Let's call them beta 1 up to beta n, such that H is equal to the sum j from 1 up to n beta j kxj. This is because we project. And second, for all I equal to 1 up to n, we know that H at point xi equal to G at point xi is equal to G at point xi, which is equal to lambda. Now put these two together, this one and this one. This means that hence sum j from 1 up to n beta j kxj at point xi is equal to h at point xi, which is lambda I, for I from 1 up to n. One more time, I write the same thing. So this is equivalent to say sum j from 1 up to n beta j k, capital K now, xi xj is equal to lambda I and the matrix form of this is equal to k xi xj. Now the matrix a from 1 up to a and j from 1 up to n times the vector beta 1 up to beta n is equal to the vector lambda 1 lambda. That's the same thing. The ice row is what written here. That's the ice row. So we see that this implies that lambda 1 up to lambda n is in the range of the matrix kx1, kxj, and by. That's one direction, and it's almost reversible, this, because, I mean, it's almost reversible. The things I wrote here, we can go backward. Now assume that lambda 1 up to the vector lambda n is in the range, and let me write G to avoid that big notation. Then pick any, then there is any solution you want. There is alpha 1 up to alpha n such that G or K xi xj times alpha 1 up to alpha n is equal to lambda 1 lambda. That's the meaning of being in the range. Now expand. That's why I said this is reversible. Instead of this form with alpha instead of beta, write it in this way. Hence, sum is precisely what is here, j from 1 up to n, k xi xj times alpha I, which I write it here, is equal to lambda I. This is true for I equal 1 up to n. That's the nth row of this identity. And put it in the function form. It's equal to sum j from 1 up to n alpha I. This is alpha j kxj. This function at point xi is equal to lambda I. That's the same thing, but written a bit differently. And then it implies that the function h j from 1 up to n alpha j kxj interpolates. So we are done. That's kind of the end of the proof, because the second part we have already seen in another proposition. The thing that H equals to T is unique minimal norm, we have already seen. And the only thing which we need to verify is this useful identity, why the norm of H is given by this. And that is why I said keep this identity, I will use it again. Norm of F is equal to G alpha scalar product with alpha. And what was alpha? Alpha is the solution of G alpha. Maybe I added somewhere here. It was G alpha equal to lambda. It should have been written somewhere in the proof. Yeah, G alpha is equal to the lambda. So I use this identity to arrive at the formula which is suggested here. Norm of H squared. So let me add it here at the end, finally. Norm of H squared is equal to, by the formula, norm of G alpha scalar product with alpha. In Cn, we have seen this before. And what was alpha? Alpha was a vector such that G alpha is equal to the lambda. You can see, very easy, if we know the formula before. That is why I suggested this identity. It's better to be mentioned as a lemma because we use it several times. The rest, uniqueness and minimal, we have seen before. So the solution here, I repeat, H equal to the sum J from 1 up to n alpha j k x j is unique. Alpha is not necessarily unique, but H is unique. It's of minimal norm, and the norm is given by this inner product in C. Kind of trivial corollary for what we have seen. The same assumption as before. I do not repeat the assumption. So the same assumption. As in theorem. But we add that, also assume that another extra assumption. G k x I x j I j from 1 up to n is invertible. We add this. So invertibility is an extra assumption here. What is the consequence? Consequence is that here, when we have G of alpha equal to lambda in this, either in this or here, we need V to be in the range. But when it's invertible, the range is all of Cn. It's always in the range. It has always a solution. So invertibility here guarantees the solution. Then for any set of points lambda 1 up to lambda n in C, there is an interpolate. There is an interpolating function. Always there is a solution. And we know how to get the minimal one and the unique. The unique interpolating function. Of minimal norm is given by the formula is given by G equal to sum alpha j k xj, where G alpha is equal to lambda. We know what is G, what is vector alpha, what is vector lambda. It's a kind of trivial corollary after of a theorem, but it also highlights the fact that there is a merit to go for kernels for which G is always invertible. And that's the content of our next section, strictly positive kernels. Before if A is an n by n matrix, we saw the meaning of A being positive. That was equivalent to say that the inner product of AX and X in Cn is always bigger than or equal to 0. That's a definition. And A bigger than 0, it means that A is bigger than or equal to 0, and moreover, AX inner product with X is 0 if and only if X is equal to 0. That's the meaning of being strictly positive. In other words, no trivial combination gives us the 0. And being strictly positive, again, from linear algebra, there is another way to characterize them. It's equivalent to being positive and invertible. Again, another way to say the same thing, it's not something really different, is being positive and all eigenvalues are strictly positive. That's equivalent to be invertible. And don't forget that we cannot remove A bigger than or equal to 0, for example. I mean, say, for example, all eigenvalues, if all eigenvalues are positive, then our matrix is positive. This is not true. We need to keep this all the time, or at least say that A is a self-adjoint. There are simple examples to say that why it's needed to keep either self-adjoint or being positive, plus something more to give us a strict positivity. And now, why strict positivity is important is this theorem, which combined with our previous corollary, you will see why we ended up with this theorem. X set and K from X times X to C a kernel, then the following are equivalent. The following are equivalent. First, K is strictly positive. I mentioned what's the meaning of a matrix to be strictly positive. It would be better to here to add what's the meaning of K being strictly positive, but I believe everybody knows. This means that, I mean, all possible n by n matrices for all n 1, 2, 3. All of them are strictly positive. That is the meaning of a kernel being strictly positive. So it's clear what it means. 2 equivalent to for any n and any set of distinct points. And any set of distinct points x1 up to xn in X. The kernel functions are linearly independent. K at point x1 up to k at point xn are linearly independent. Three. Again, this is a theorem which shows somehow the connection between linear algebra and function theory. Being linearly independent, well, you can say that it's a question in function spaces also, even though it has a flavor of linear algebra because we talk about linear independence. Look at the next one, number 3, and also number 4. For any n, and any set of distinct points, x1 up to xn in X, and any set of scalars, no restriction. So any alpha 1 up to alpha n in C. So any set of scalars that are not all equal to 0. That's the usual assumption for linear independence. Equal to 0. There exists an f in H with the combination alpha 1 f at point x1, alpha n f at point xn not equal to 0. In other words, there is no linear dependence between elements of f evaluated, element of H evaluated at point x1 up to xn. Recalling again the Sobel of space is a good idea. And finally, something from analysis that it happens in other contexts too. For any n and for any x1 up to xn, there exists g1 up to gn, n function in H, such that gi at point xj is equal to delta ij, the Kronecker notation, or put it this way explicitly, 1 or 0, I is equal to j, and if not. So this is the interconnection between, I mean, at least 4 concepts. And at the end of the day, all of them are different features for strict positivity. So in some spaces, for example, number 3 is equal to verify, and in some others, number 4. Before giving the proof, consider examples. Our H to be either Hardy space H2 or Bergman space A2 or Dirichlet space D that we saw in chapter 1. Do you agree immediately that number 4, the condition 4, is valid for all of them? In Hardy space, in A2, and also in the Dirichlet space. They are defined on the open unit disk. And if I give you endpoints distinct on the open unit disk for any Z1 up to Zn on the open unit disk distinct, you can easily find functions. There is such that what is your candidate? We have seen in one occasion this candidate before. Recall that these are function spaces of on the open unit disk, holomorphic ones, and therefore polynomials are there. Polynomials are in H2, are in the Bergman space A2, and also in the Dirichlet space. And the candidate is GI of Z to be Z minus Z1, Z minus Z2, and we just remove Z minus ZI. So we go Z minus ZI minus 1. So this already satisfies the property that GI at point Z1, Z2, up to Zn, except Zi is equal to 0. And if you want to normalize at point Zi, just add Zi minus Z1, Zi minus Zi minus 1, Zi minus normalization. So this function satisfies the property that we want. So it is very easy to verify for these 3 spaces and many more that we have number 4. And again, Sobolev space. So in H2, in A2, and in D, our kernel is strictly positive. Let me add here. So the kernels, they are different kernels. The kernels of H2, A2, and D are strictly positive. However, in the Sobolev space, either number 2 or number 3. Number 2 is easier. We don't have number 2. Does not work. We have k at point 0 minus k at point 1 is equal to 0. So it's linearly dependent, and therefore k, the kernel of this space, is not strictly positive. So, and I mean, all examples that we have seen up to now, it's easier to verify one of these conditions to conclude that if the kernel is strictly positive or is not strictly positive. Well, It's 14:55. Oh, I put the proof for after the break. So let's have a 10-minute break and then we continue.